Ever wonder how you track something moving thousands of miles an hour? I mean, it sounds like something straight out of science fiction, but it is a very real-world problem, and that's exactly what we're diving into today. The incredible science of seeing the invisible, specifically that fiery trail left behind by the fastest objects we've ever built.
You know, this isn't just some abstract puzzle. It's a critical challenge for defense systems all over the world. When you get to hypersonic speeds, your normal, everyday tracking methods, they just don't work. So the real question becomes, how in the world do you see something that's moving way too fast to be seen?
Well, the secret, it turns out, isn't in looking at the rocket itself, but at the enormous, superheated trail it leaves behind. That exhaust plume, that is the key. It's the target for detection, for identification, and for tracking. It's like a giant fiery signature in the sky, but here's the catch. Most of its secrets are completely invisible to the naked eye.
Okay, so every single hot object, whether it's your morning cup of coffee or a massive rocket engine, gives off infrared radiation. Think of it like a unique heat fingerprint. And by analyzing this infrared signature, scientists can learn a ton about the rocket. But first, they have to know exactly what they're looking at.
So you might be thinking, why not just launch a bunch of rockets and measure their heat? Well, if only it were that simple. This brings us to a huge hurdle for scientists in this field, something they call the scaling problem.
So here's the dilemma. On one hand, yeah, you could test a full-scale rocket. You'd get perfectly accurate data. But it's also unbelievably expensive and, frankly, pretty dangerous. On the other hand, you've got small-scale models or computer simulations. They're way cheaper, they're perfectly safe. But the big, looming question is always, can you actually trust the data?
And that right there is the million-dollar question. How can you be sure that what you learn from a little 1-foot model in a lab actually tells you anything real about a 100-foot rocket tearing through the atmosphere? Cracking this nut is the key to making predictions that are both affordable and reliable.
So, what's the solution? Well, it starts with building an incredibly sophisticated computer simulation, what you might call a digital twin of the rocket plume that you can test and poke and prod in a totally virtual environment.
And here it is. Welcome to the digital laboratory. The simulation kicks off with a pretty basic-looking 2D model. You can see the nozzle, that's where the exhaust shoots out. You've got the inflow of air from around it, and then the outflow, the plume itself. It might look simple, but it's a really powerful way to represent real-world physics.
Now, under the hood, this simulation is crunching some seriously complex numbers using something called Computational Fluid Dynamics, or CFD. The easiest way to think about it is like a virtual wind tunnel that models every single tiny aspect of the plume. We're talking its temperature, its pressure, and all the crazy chemical reactions happening inside that fiery jet. But how do you know the simulation's actually right? Well, here's the proof. That dotted line you see? That's data from a real-world physical experiment. And the solid red line? That's what the simulation predicted. I mean, look at that. The match is almost perfect. That's how you know you can trust your digital model.
Now that they had a simulation they could trust, the scientists could start asking some really deep questions, and they zeroed in on one critical factor that, it turns out, dramatically changes everything. It's a phenomenon called the afterburning effect.
So what on earth is afterburning? Well, rocket engines aren't perfectly efficient. They shoot out a bunch of unburned fuel, gases like hydrogen and carbon monoxide. And when that superheated gas hits the oxygen in the atmosphere, it ignites outside of the engine. It's almost like the plume takes a fiery second breath.
To prove just how big a deal this afterburning is, the researchers ran this really clever experiment inside their simulation. They modeled the plume in two totally different atmospheres. First, in just normal air, with plenty of oxygen. And second, in an environment of pure nitrogen, where there's no oxygen at all to fuel that secondary fire.
And wow, the result is just staggering. On the left, in that nitrogen environment, you see the plume's heat signature without any afterburning, but on the right, in normal air, it's a night and day difference. Afterburning creates a much larger, hotter, and way brighter infrared signature.
So how much brighter are we talking? The research found that afterburning can crank up the peak radiance, basically the brightness of the heat signature, by up to 10.21%. Now, that might not sound like a huge number, but trust me, in the world of detection and tracking, a 10% brighter signal is a massive difference.
This whole discovery about afterburning, it was the final piece of the puzzle. It's what allowed the researchers to finally connect the dots between the tiny models and the real thing, and discover a universal scaling law.
This all led them to the ultimate question, the one that ties everything back to that original problem.
Does this powerful afterburning effect behave differently as the size of the rocket engine scales up?
All right, let's just watch what happens as we scale this thing up. Here at just 1/10 of the standard scale, you can see the afterburning effect. It's there, but it's pretty small, pretty limited.
Okay, now we're at the standard 1.0 scale. See that? The afterburning region is way more obvious now. The effect is clearly getting stronger.
And here we are at 5 times the scale. Whoa! The afterburning effect is now dramatically enlarging the plume's entire heat signature. It's definitely not some minor factor anymore. And finally, at 10 times the scale, the change is just undeniable. At this point, the heat from afterburning has become the single most dominant feature of the plume. So the takeaway is crystal clear. The bigger the rocket gets, the more important afterburning becomes.
And here it is, the big breakthrough. This wasn't just some random increase. The researchers found a predictable, mathematical rule. As they put it, the relationship between the engine scale and radiation intensity is exponential. In other words, it doesn't just add, it multiplies.
This exponential law is like finding a Rosetta Stone for rocket science. It gives you the key to translate the results from small, safe, cheap lab models into incredibly accurate predictions for massive, full-scale rockets. It completely solves that scaling problem they started out with.
What this all shows is how a really deep understanding of physics can uncover these beautiful, predictable patterns in what seems like a totally chaotic system. And it really makes you wonder, right? If we can decode the invisible signature of heat, what other incredible secrets are just hiding in plain sight, waiting for us to figure them out?